So in this video, we're going to talk about how to select an appropriate model to represent data. So what you can do is you can actually look at a table of values and determine whether you have a linear, quadratic, or exponential function. All you need to do is look at the pattern in the y values. So let's see how that works by looking at these three examples. So here I have the table of a linear function, I have the table of a quadratic, and the table of an exponential. You can look at the y values and see that there's a pattern in each one of these functions. So happens in a linear function is you're going to be adding or subtracting the same value every time. So you see when I go from 1 to 3 here, I have a change of plus 2. From 3 to 5, I have a change of plus 2. 5 to 7 is plus 2. And then 7 to 9 is going to be plus 2. This change in the y values is called the first difference. And that's actually going to be constant when you have a linear function. Okay, so the first difference will be constant. What happens in a quadratic? So in a quadratic, let's look at the first difference. So from 5 to 4, I have minus 1. From 4 to 5, I have plus 1. 5 to 8, I have plus 3. 8 to 13, I have plus 5. So you see, I don't have a constant first difference. But if I look at the second difference, which is the change in these values, you can see that I have plus 2. Here I have plus 2. And then here I have plus 2. So that means that my second difference, okay, so the change in the change is going to be constant when you have a quadratic function. Okay, what about exponential? In exponential, you're going to be multiplying by the same value every time. And you can figure that value out by taking a y value and dividing it by the previous one. So if I do 1.5 divided by 0.75, that gives me 2. Okay, so here to get from one y value to the next, I need to multiply by 2. If I do 3 divided by 1.5, that gives me 2. So once again, multiply by 2. If I do 6 divided by 3, that gives me 2. So multiply by 2. And then 12 divided by 6 once again gives me 2. So I'm multiplying by 2. Okay, so what happens in an exponential function is you have something called the common ratio. And that's what you'll see in those y values. Okay, so you'll see three different patterns when you're looking at linear, quadratic, and exponential functions. So just to summarize, in a linear, you'll be adding or subtracting the same number every time. Quadratic, the second differences will be the same. Exponential, you'll have a common ratio. So when you're using real life data and you start off by creating your scatter plot, you can sometimes see from the shape of the graph whether you have linear, quadratic, or exponential. In linear, you'll see the data follows like approximately a line. Quadratic, you'll start to see kind of this parabolic shape. And in exponential, you'll see a shape like this. Sometimes just by looking at the scatter plot, it can be hard to tell the difference between quadratic and exponential. That's why you need to really rely on the table of values and look at the pattern there. But the graph can give you a clue to start off with. So let's look at this table right here and determine whether the appropriate model is linear, quadratic, or exponential. So I'm going to start off by creating the scatter plot just so I can get a visual of what this data is going to look like. So I'm going to go ahead and type in all these values. Okay, so you can see it kind of starts to look like a line, right? So I'm thinking linear is probably going to be a good fit for this data, but I'm going to go ahead and figure out the pattern just to make sure that I've determined this correctly. So what I need to do is I need to take these values and subtract them from the previous one. So I have 7.2 minus 5.1, that gives me a change of plus 2.1. Okay, and then I do, let's see, 9.1 minus 7.2, and that's going to give me a change of plus 1.9. And then I have 10.9 minus 9.1, and that gives me plus 1.8. And then finally, I have now 12.8 minus 10.9, and that gives me plus 1.9. Okay, so you can see the rate of change is about 2, right? It's approximately 2 every time. You won't have the exact value whenever you're working with real life data, but I'm thinking that linear is a pretty good fit. We have another way of checking if this is a good fit for our data. Remember, once we do the regression, if you look at the R value, you see that's very, very close to 1. And this graph, in fact, does pass through most of my data points. So I'm going to say that this is going to be linear, right? Because my R value is 1. So linear is going to be a good data model. Okay. And I can actually go ahead now and write the equation that's going to fit this data. I have 1.91x plus 3.29. So now let's look at this data here and determine whether the appropriate model is linear, quadratic, or exponential. So I'm going to start off by creating this scatter plot, and then I'm going to go ahead and type in these values. So you can see here, there's kind of like this curve to my data points, right? So I'm thinking it's going to be, it looks more exponential than quadratic, but remember, I want to double check my table to make sure that it works. I don't think it's going to be linear. But let's go ahead and look at the y values to see what's going on here. So from 4 to 5, I have a change of +1. From 5 to 6.24, I have a change of +1.24. Let's look at the change from these 2 points. So I do 7.7 minus 6.24. That's about plus 1.46. And then from 9.75, I subtract 7.7 and I have plus 2.05. So you can see this rate of change is changing, so it's not linear. But let's look at the second differences to see if it's going to be quadratic. So from 1 to 1.24, I have a change of plus 0.24. Let's do now 1.46 minus 1.24. That's a change of plus 0.22. From 2.05, I subtract 1.46, and that gives me plus 0.59. Okay, so my second difference is also not the same. So quadratic looks like it's not going to work either. I don't want to just assume it's exponential. I'm going to look at the change. So I'm going to do 5 divided by 4, and 5 divided by 4 is 1.25. Then I do 6.24 divided by 5. And let's see what value that gives me. That's about 1.25 again. If I do 7.7 divided by 6.24, that's about 1.23. And then I'm going to do 9.75 divided by 7.7. And let's go ahead and do that on our calculator. 9.75 divided by 7.7 is about 1.27. So you can see, although it's not the exact same value, it's approximately the same ratio every time. So let's go ahead and make sure that coefficient of determination is telling us this exponential regression is a good model. You can see that's very close to 1, right? So that means that this exponential equation, y equals 3.19 times 1.25 to the x, is going to be a very good fit for this data. Okay, so this one is going to be exponential. Now let's try this example. So here we have another table of values. So I'm going to start off by creating this table in Desmos so I can see the scatter plot. Okay, so I don't think it's going to be linear. It actually kind of does look like a quadratic, right? It kind of looks like half a parabola. Let's go ahead, check now the values and see what's going on here with the rate of change. So if we do 5.2 minus 4.1, that rate of change is going to be plus 1.1. If we do 7.9 minus 5.2, that's going to be a change of plus 2.7. If we do 12.8 minus 7.9, that's going to be a change of plus 4.9. If we do 20.2 minus 12.8, it's going to be a change of plus 7.4. Okay, so you can see quickly it's not linear. There's not a constant rate of change. So let's look at the second difference now. So I'm going to find the difference in these change values. So I do 2.7 minus 1.1. That's going to be a change of plus 1.6. If I do 4.9 minus 2.7, that's going to be a change of plus 2.2. If I do 7.4 minus 4.9, that's going to be about plus 2.5. Okay, so you can see it's approximately 2. It's not exactly 2 every time. So thinking quadratic might be a good model, but let's just try exponential to make sure. So if we do 5.2 divided by 4.1, that's going to give us about 1.27. If we do 7.9 divided by 5.2, That gives us 1.52. So I can already see these common ratios are very different. But I can just, keep trying them if I want to. 12.8 divided by 7.9. That's 1.62. And then I have 20.2 divided by 12.8. And that's 1.58. Okay, so I think quadratic is the better model for this data set, just because the second difference is approximately around the same value. Just to make sure, I can just go ahead and do the regression and then ask Desmos to tell me if it's a good fit. You see here, it gives me the quadratic and it says that r squared is 0.9995. So that means that quadratic equation is going to be a good fit for this data. Okay, so we have 1.06 x squared minus 2.36x plus 5.5. Okay, and that's going to be a good fit for this data set. So remember, by viewing the scatter plot and studying the values in the table, you can determine whether a linear, quadratic, or exponential function will best model a data set.